At the edge of a national forest in the American West, a ranger once cut into a fallen pine to count its rings. The trunk lay clean and straight across the ground, its cross-section exposed like a clock face. Each ring formed a perfect circle. Each circle marked a year. But what caught his attention was not the number, it was the uniformity. The trees surrounding him, stretching for miles in every direction, all seemed to share the same age. Not similar, nearly identical. A forest that should have grown in layers across centuries appeared to have begun at once, as if time itself had been reset across the landscape. The accepted explanation is simple. Most forests, especially in North America and Europe, are considered second growth. Logging, fire, and settlement cleared vast areas in the 19th and early 20th centuries. Governments later replanted them. Agencies kept records. Seedlings were distributed. Nurseries expanded. Conservation programs restored what industry removed. The timeline fits neatly into textbooks. Forests were cut. Forests returned. Nature healed. But the record shows details that sit uneasily inside that story. When foresters began systematic surveys in the early 20th century, they often reported stands of trees with remarkably synchronized ages, even in regions where no documented clear-cutting had occurred. Remote valleys, mountain slopes, protected reserves, places with little access to heavy machinery. The trees there did not display the layered structure expected from natural succession. Instead, they formed even canopies, evenly spaced trunks, and synchronized lifespans. The landscape looked organic. The numbers looked engineered. So a quieter theory began to circulate among field researchers, surveyors, and independent historians. Not a dramatic claim of secret plots or hidden cabals. A simpler possibility, that the modern forests covering large portions of the earth are not remnants of ancient wilderness, but regrowth after a widespread clearing event far larger than conventional history describes. That what we call forests today may be younger than assumed. That the absence of truly old trees is not coincidence. It is a pattern. The first clues often appear in measurements. Dendrochronology, the science of dating trees by their rings, allows precise calculation of age. In many national forests, the oldest trees cluster within narrow age ranges: 100 years, 120, occasionally 150. Truly ancient specimens, those exceeding 300 years, exist, but remain rare and isolated. Even in regions considered untouched for centuries, vast tracts display similar growth timelines. The record shows synchronized beginnings across distances too large to attribute to local disturbance alone. Old photographs deepen the puzzle. Early 20th century survey images depict landscapes now dense with trees, yet at the time nearly barren. Hillsides appear open. River valleys show sparse vegetation. The terrain looks stripped to soil and rock. Within a few decades, those same locations transformed into uniform forests. Growth occurred rapidly and consistently, producing even stands rather than the chaotic layering typical of untouched ecosystems. The change was not gradual, it was sudden. Maps provide another layer of evidence. Cartographers in the 18th and early 19th centuries often described extensive open land where modern maps show continuous forest cover. Terms such as barrens, scrub, and brush appear frequently in official surveys. These labels did not indicate lush woodland. They referred to low vegetation, sparse growth, bush-level ecology. When later maps replaced those descriptions with dense forest symbols, the transition occurred within a surprisingly short historical window. The official explanation acknowledges much of this history. Logging did remove enormous quantities of timber. Fires, both natural and industrial, reshaped landscapes. Agricultural expansion cleared millions of acres. These forces are well documented. They explain why forests in many regions share similar ages. The record supports that conclusion, but the explanation struggles to address areas where no corresponding documentation exists. Remote plateaus, protected reserves established before large-scale industry, mountain regions with limited human settlement. In these places, synchronized tree ages still appear. Consider the spacing of trees in managed forests. Foresters plant seedlings in regular intervals to maximize growth and reduce competition. The result is predictable geometry. Rows form. Canopies align. The pattern is efficient and measurable. Yet similar spacing appears in forests officially classified as natural. Trunks stand at consistent distances from one another. Underbrush develops evenly. The structure resembles cultivation rather than random growth. The resemblance is subtle but persistent. Engineering records reveal how quickly landscapes can change when large-scale clearing occurs. In the late 19th century, logging operations in North America removed billions of board feet of timber annually. Rail networks expanded into remote regions. Portable sawmills followed. Entire hillsides disappeared within a few seasons. Contemporary newspapers described mountains stripped bare, soil exposed to sun and wind, rivers choked with debris. The transformation was visible from miles away. The capacity existed to reshape entire ecosystems in a single generation. Yet the pattern repeats beyond industrial centers. Satellite imagery of modern forests across continents shows synchronized canopy heights and consistent density. Europe, Asia, North America, and parts of the Southern Hemisphere display similar growth timelines. Different climates, different soils, similar age distributions. The pattern does not disappear when borders change. It expands. Historical climate records introduce another factor. The late 19th century experienced unusual environmental stress in many regions. Drought cycles intensified. Wildfires increased in frequency and scale. Volcanic eruptions altered atmospheric conditions. Agricultural failures spread across continents. Governments recorded widespread land degradation. In response, large reforestation campaigns began. Seeds were distributed by the ton. Millions of saplings entered the ground within a few decades. The scale was unprecedented. What matters is not whether those programs existed. They did. The question is whether their reach extended further than official summaries acknowledge. Archival documents from forestry departments often describe emergency planting initiatives covering vast territories. Reports mention aerial seeding experiments, coordinated burn suppression policies, and soil stabilization efforts. These measures reshaped landscapes quickly and quietly. The public saw green returning. The record shows intervention. Another clue lies beneath the surface. Soil analysis in many forested regions reveals layers of charcoal and ash beneath current root systems. These layers indicate intense fires or clearing events predating the growth of existing trees. The deposits appear continuous across large areas rather than isolated patches. In some cases, the ash layer sits directly below the oldest living roots, suggesting that regeneration began immediately after a widespread disturbance. The soil remembers. Eyewitness accounts from early settlers describe vast stretches of land with few mature trees. Journals speak of open plains where modern visitors expect dense forest. Travelers reported long distances traveled without shade. They described horizons unobstructed by tall timber. These observations appear repeatedly across diaries, military surveys, and agricultural reports. The language is consistent. The landscape looked empty. Geological surveys add another dimension. In regions where forests appear continuous today, sediment layers often contain pollen records indicating periods of reduced tree presence. These gaps correspond with known historical disruptions such as fires, disease outbreaks, or climatic shifts. But some gaps extend across regions larger than any single documented event. The cause remains uncertain. The timeline remains compressed. Economic incentives also played a role in shaping the narrative. Governments dependent on timber revenue had reason to promote the idea of sustainable renewal. A forest reborn suggests stability. It reassures investors and citizens. It supports the belief that natural resources regenerate reliably. Bureaucratic language tends to simplify complex transitions. Reports summarize recovery rather than disruption. Over time, simplified explanations become accepted history. None of this requires a hidden conspiracy. Large institutions manage vast territories through standardized categories: forest, farmland, reserve, wilderness. These labels help organize land use. They do not capture every transformation. When records become fragmented, administrators rely on assumptions. Data gaps fill with generalizations. The result is continuity on paper even when the landscape changed abruptly. Inertia replaces investigation. The repetition of uniform tree ages across continents raises a broader question. If modern forests are largely young, what existed before them? Were ancient forests removed gradually through centuries of use? Or did a more concentrated period of disturbance reset ecosystems within a relatively short span of time? The difference matters. One scenario reflects slow adaptation. The other suggests sudden change. Infrastructure offers another hint. Many regions once supported extensive networks of logging railways and temporary settlements that vanished after operations ended. Maps from the early 20th century show dense grids of tracks penetrating deep into wilderness areas. Today, those lines have disappeared beneath vegetation. Their presence indicates industrial reach far beyond populated centers. The absence of visible remains can create the illusion of untouched nature. Photographs from that era capture scenes difficult to reconcile with modern expectations. Entire valleys reduced to stumps. Mountainsides stripped to bare soil. Rivers running dark with sediment. Workers standing atop piles of timber taller than buildings. These images are not rare. They are archived in libraries and government collections. The record is still there. One must also consider the biological limits of tree growth. Even fast-growing species require decades to reach maturity. For millions of acres to display synchronized height and density, regeneration must begin simultaneously across large territories. Natural processes rarely operate with such precision. Disturbances vary. Soil conditions differ. Seed distribution fluctuates. Yet the forests often appear uniform from horizon to horizon. The mainstream scientific explanation emphasizes ecological succession. After disturbance, pioneer species colonize open land. Over time, diverse communities emerge. Eventually, mature forest returns. This model describes many environments accurately. It accounts for gradual transitions and mixed age structures. But when entire regions show narrow age ranges and consistent spacing, the model leaves unanswered questions. Succession predicts diversity. Uniformity suggests coordination. Legal definitions reveal another piece of the puzzle. In many countries, land classified as forest does not require old-growth conditions. A minimum percentage of tree cover qualifies the area for that designation. Young plantations and natural woodland receive the same label. Statistical reports therefore describe expanding forest cover even when the average age of trees declines. The terminology creates continuity where history shows replacement. The pattern widens when examined globally. Remote sensing data from international agencies indicates that large portions of the world's forests regenerated during the 20th century. The timing aligns with industrial expansion, agricultural abandonment, and government reforestation programs. Regions separated by oceans display parallel timelines. The causes differ locally. The outcome remains consistent. Young forests dominate. There is also the question of scale. Clearing events large enough to reset ecosystems across continents would require enormous energy and coordination. Industrial logging provides one explanation. Climate-driven fires offer another. Disease outbreaks could contribute. Each factor leaves traces: burn scars, economic records, mortality reports. When these traces overlap in time, they create a cumulative effect capable of reshaping entire landscapes. What remains is not mystery alone, but accumulation. Measurements align. Photographs align. Maps align. Soil layers align. Administrative records align. Each piece supports the possibility of widespread clearing followed by synchronized regrowth. None proves the theory independently. Together, they form a pattern difficult to ignore. The stone remembers. The soil remembers. The record remembers. What changed was the explanation. Modern forests appear ancient because they feel timeless. Trees rise quietly. Seasons repeat. The canopy closes overhead and hides the ground below. Memory fades beneath leaves and bark. But the numbers remain measurable. The timelines remain visible. The absence of truly old trees across vast territories is not an illusion. It is data. If the majority of forests on Earth are younger than commonly believed, then our understanding of ecological history shifts. Conservation strategies change. Carbon calculations change. The narrative of uninterrupted wilderness becomes a story of recovery after disruption. A green landscape becomes evidence of resilience rather than permanence. The question is not whether forests exist. They do. The question is how long they have stood and what came before them. Because when tree rings align across continents, when soil layers reveal sudden resets, and when historical records describe barren land where dense forest now grows, the pattern does not disappear. It waits. And the real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.